Now, do you all agree that the electric field should have this form? Assuming that the cylinder is very long, so that its electric field is almost equal to the electric field created by an infinite cylinder. Now, to practically use the Gauss law, you first have to determine the shape of the electric field. I mean, without knowing how the electric field looks like, you cannot determine what kind of a surface you have to choose. Now, this tells me that the electric field depends on, the magnitude of the electric field at least, depends only on the distance from the central axis of the cylinder. So if I choose points that are, if I choose a surface such that every point on the surface is at the same distance from the central axis, then the magnitude of this electric field at least will be constant. Since it's a constant, I can take it out of the integral. Remember the expression of the Gauss law. This integral around the closed surface is equal to the enclosed charge divided by epsilon 0. This is the Gauss law we have. You see, we don't know the electric field. This is an unknown function. You cannot take the integral of an unknown function. So since we cannot take the integral of an unknown function, we have to somehow take that unknown function out of the integral. So if we can take that unknown function out of the integral, then we can evaluate what remains. Now, I already know that on a cylinder, on the sides of the cylinder, not at the top or the bottom, on the sides of the cylinder, the magnitude of the electric field is a constant. So if I apply the Gauss law on this cylinder, I can at least take the magnitude of the electric field out of my integral. What remains will be a rho vector, and well, rho vector, once I know the cylinder, I know what the rho hat vector is, I know what ds is. In principle, I can evaluate the remaining integral. The only unknown, which is the magnitude of the electric field, it is out of this integral. Now we will have to resolve one complication though. This will be my surface. As your friends pointed out, it will be a cylinder. Of course, to apply the Gauss law, I have to take a closed surface. A cylinder, an infinite cylinder is not a closed surface. I have to take a closed one. So I close the top and the bottom of the cylinder. So I choose this as my cylinder, as my Gauss surface. Its radius is, let's say, rho. I know that at every point on this surface, the electric field its magnitude depends on rho, which is just a constant on the sides, and it is in the rho hat direction. Now let's consider this integral, E dot ds. Well, over this closed cylinder with the top and the bottom parts. Now this has contributions from the top. It has contributions from the bottom. And it has contributions from the side. I'm imagining this closed cylinder, top and the bottom are closed, so I receive contributions from everywhere. From the top, from the bottom, from the sides, in principle. But let's see, if you look at the top, this is my cylinder. Now, what is the direction of ds on the top? It is pointing upward. What is the direction of the electric field? It's horizontal in some direction. Whatever the direction is, the angle between the two is 90 degrees. So this is my ds vector, this is my E vector. The angle between them is 90 degrees. So since this E vector and the S vector, they are perpendicular to each other, their scalar product would be 0. So this is 0. Now if I look at the bottom surface, what is the direction of the S on the bottom? It's pointing downward. Again, the electric field is horizontal, either this way or this way or this way. They are again 90 degrees with each other. So this is again 0 at the bottom. So I only receive contribution from the sides. Now, on the sides, what is the direction of ds? Well, here it is in this direction, here it is in this direction, here it will be in this direction. It's in the direction of rho hat. So ds is its magnitude in the rho hat direction. E is its, let's say, magnitude in the rho hat direction. So E dot ds is equal to E rho times ds. So when I consider this closed integral, this integral over the closed surface, first of all, I only receive contribution from the sides, and the contribution from the sides can be written as E of rho times ds over the sides only. I only receive contributions from the sides. But you see, now, since we already know that the electric field depends only on, since we have chosen a cylinder, and on the sides of this cylinder, rho is a constant. That is why we had to choose a cylinder, because rho is a constant. Since rho is a constant, the magnitude of the electric field on the sides of the cylinder is a constant, so I can just take it out of the integration sign. What remains is nothing but the total area of the sides of the cylinder, which is, let's say the height is L. The side area is 2 pi rho times L. So this is E dot ds. I could evaluate E dot ds explicitly because it only depends on, it turned out that if I choose a cylinder, it depends only on rho, which is a constant on the cylinder. For any other surface for which rho can be changed, if we chose another surface such that the rho changes as we move around the surface, we couldn't take E of rho out of this integration sign. That is why we had to choose a cylinder and not anything else. Now we can go back to our Gauss law. E rho 2 pi rho times L is equal to, what is enclosed charge? Let's say this cylinder, the original, our capacitor, has a height, let's say h. What is Q enclosed? I have a total charge Q in the inner cylinder. It is distributed over a length h, but my Gauss surface only contains the length L of this times 1 over epsilon 0. So we know that E of rho is equal to 1 over 2 pi epsilon 0 Q over H times 1 over rho. Okay, which part? Do you have any questions about this slide? Anybody? Could you follow what we had done in this slide? We are only evaluating E dot ds. Now you see, well, let me draw them together. Let's go back to this slide. This is what I call H. And this is what I call L. I have my two cylinders. I choose a Gauss surface inside, which is also a cylinder, but a shorter cylinder. I mean, I could have chosen H is equal to L, that's not a, it's up to me. I could have chosen it. But they don't have to be equal. No, we didn't say that the cylinders are infinite. The cylinders are have a finite length. What we had said that the cylinders are very long. They are so long that the electric field inside these, between these two cylinders is, at least in most of the volume of the cylinder, is the same as the electric field created by an infinite cylinder. And then we said that, okay, if this is true, then we can assume that the electric field lines between these two cylinders are always horizontal in the rho hat direction. So at that point, after that point at least, we are always working with finite size cylinders. This is an approximation. You see, this is an approximation which is exact only in the limit that the cylinders are infinite. But in this case, we have finite cylinders. Nevertheless, we will assume that they are so long compared to their separation that this is still a good approximation for our finite cylinders. That's an assumption that we are making. So let's see, Q enclosed within this cell, within this cylinder. Well, we have a total charge plus Q in the inner cylinder. We are assuming that it is uniformly distributed in the surface. So per unit length, it is also uniform. So Q over H is the charge per unit length of this inner cylinder. But only a length large L is within my Gauss surface. So the total charge is the charge per unit length times the length that is inside my cylinder. This is our Q enclosed. If I had chosen H and L to be equal, Q enclosed would have been just large Q. Why do I need the volume? Okay, so I didn't even use an area. The only thing I used was, I'm assuming that the charge is distributed uniformly. So if I take some length at the bottom of my cylinder, it will have the same charge with the same length at the top of the cylinder or in the middle of the cylinder. That is the only thing I need. Why should it be? I mean, in nowhere the radius entered into the calculation yet. This result is independent of the radius. Now the radius will be important in a moment. But the electric field within these two cylinders is independent of the radius, as long as the total charge is the same, is kept constant. What happens is if you have a radius that is smaller, then the charge per unit area will be much larger, but nevertheless it will not have any effect on the electric field. Almost no effect on the electric field. What is the electric field inside the inner cylinder? Why? You see, I have this cylinder. Let's say the inner cylinder. This is the inner cylinder. What is the electric field inside? Okay, I have a zero, I have an infinite. Which one? No, I don't care about the center. I want to, in some arbitrary point. Let's say I have, this is the outer cylinder, this is the inner cylinder. What is the electric field here? No, there's no point charge. I only have the cylinders. I don't care, I'm not looking from a far away. I'm going and using a microscope to look at from a very small, close distance. It is 0. Because you see, we said that E is equal to E of rho hat, only using the cylindrical symmetry. We didn't use we didn't use anything other than the cylindrical symmetry of the system. The system has a cylindrical symmetry, whether you are here or in between the cylinders. The system should have a cylindrical symmetry. And since we had this cylindrical symmetry, we had used a cylindrical Gauss surface. So I can just imagine a cylindrical Gauss surface that is inside the inner cylinder. I can take such a Gauss surface, but for this Gauss surface, Q enclosed will be 0. And E dot ds will again be E of rho times 2 pi rho times L. No, yes. This is rho. E dot ds will still have this expression. Q enclosed will be 0, so this expression has to be equal to 0 over epsilon 0. Which just tells me that E of rho should be 0 inside my cylinder, inside the inner cylinder. The same thing holds if I take a Gauss surface outside my outer cylinder. Because if I take a Gauss surface outside the outer cylinder, it will have a plus Q charge in the inner cylinder, a minus Q charge on the outer cylinder. The total charge will be 0. But I warn you, I'm not saying that electric field is 0 because E dot ds is 0. It doesn't have to be. Electric field has cylindrical symmetry. Furthermore, around the cylinder, E dot ds is 0. If I have these two ingredients, then the electric field has to be 0. I have to put some additional ingredient to conclude that the electric field is 0 if E dot ds is 0. It's not always true. No. No. Well, you see, what happens here is the charges in the inner cylinder is not in the inner surface. They are on the outer surface. So I have some charges in the outer surface. Outer surface of the inner cylinder, from which electric field lines they go out. And the outer surface have electric charges on the inner surface. So whatever electric field line starts from the inner shell, it starts here, it terminates on the outer shell. Now, why do we have electric field 0 over here? Let's just imagine any cylinder or a sphere. We have an electric field at this point. We are saying that this is 0 if the electric field is uniform. So if you just, for example, consider these two cones. I mean, you can just consider any such lines. I mean, they don't have to be so symmetric. Let's say we have positive charges over here. All these positive charges will create an electric field in this direction. And all the positive charges on this side will create an electric field on the other direction. Now, I have more charges over here, but they are at a further away distance. Here I have less charges, but they are closer. And it turns out that the electric field that these two charges create, they have equal magnitude and opposite direction, so they just cancel. That's why I don't have any electric field inside. Now let's go back to our initial problem. We had a system of cylinders. We already calculated the electric field. One over 2 pi epsilon 0 q over h 1 over rho in the rho hat direction. Remember, we are interested in the capacitance of the system. What is the capacitance? And to calculate the capacitance, what is the potential difference between the inner and the outer cylinders? That is what we need to calculate now. Since we know the electric field, we can calculate the potential difference. It will be an integral from some point outside to some point inside. Of E dot dl. Well, the potential difference here is actually the magnitude of this one. In defining the capacitance, this is the magnitude. It cannot be negative. At least for the moment, we will always take it to be positive. Now, let's look at from the top. It will be easier to evaluate this integral. This is one point, this is another point. Well, the easiest trajectory to go from the point A to point B would be, for example, go along the radial line and then to the point B. Here, in this region, the electric field is 0, so I don't have any contribution. So I will only have contribution along this segment. Let us take a very small part, a very small segment on that trajectory. This is dl, which will be, let's say, dl in the rho hat direction. Oh, sorry. dl is less than 0. Now the electric field is 1 over 2 pi epsilon 0 q over h 1 over rho in the rho hat direction. So we already know E dot dl, which is 1 over 2 pi epsilon 0 q over h 1 over rho. dl, let's define dl. Instead of dl, let's call it d rho. Why d rho is basically the change in the rho as we go from one end of our segment to the other end, times d rho. This is our E dot dl. This is equal to 1 over 2 pi epsilon 0 q over h d rho over rho. What is the initial value of rho? Now we had defined it as, let's see, b. The outer radius is b. This is b. This is a. The initial value of rho at the beginning of the trajectory is b. And the final value of rho at the end of the trajectory is only a. And we started from b. We are going up to this point, which is a. This point has rho is equal to a. And so we are finally done. V is equal to 1 over 2 pi epsilon 0 q over h logarithm of b over a, which should be equal to q over c. And so finally we are done. We know what c is. C is the inverse of 1 over 2 pi epsilon 0, 1 over h logarithm of b over a. Questions? Which one? This is V. We calculated the potential difference. And the definition of the capacitance is that the potential difference should be equal to charge over the capacitance. Sure. So we have the capacitance is equal to 2 pi epsilon 0 h over logarithm of P over A. This is our capacitance. I took the absolute value. Other questions? Which one? The row. This one. So as you go from this point to this point, your distance from the central axis, is it increasing or decreasing? It's decreasing. So the change in rho is negative as you go from this point to this point. The rho, by the way, is not the magnitude of the EL. The magnitude of the EL is minus the rho, since the rho is negative. Other questions? Are you sure you don't have any other questions? Okay, this is not the charge. Yes, you have a question. We are still we are having questions. So if the charges are different, then what happens? Is that your question? Oh, so your friend is asking this question. So suppose we have one plate like this, and then a smaller plate. You put a plus Q charge and a minus Q charge over here. Then you have to calculate V. Yeah, it will be a lengthy calculation, which you will be able to do in your third year. But whatever you obtain, it will be proportional to Q, and the proportionality constant you define as 1 over C. No. So the problem is, it's quite hard. I mean, you see, if you have such a configuration, one of the problems is that the charge distribution will not be uniform, and you cannot even assume it is approximately uniform if the areas are different. Now, if you assume this to be a point charge, and this is a very large plate, then you can still make a calculation. You remember in one of the homeworks, you were given the electric field created by a point charge and an infinite plate. You were given the electric field. You can use that electric field to calculate the potential difference between the plate and the capacitor and the point charge, and then that would allow you to evaluate the capacitance explicitly. But for the general case, an explicit calculation even in the third year will not be possible. No, that will be the quiz. Something along those lines will be the quiz. No. You see, the main difference between a battery and the capacitor, quite a number of you were asking that. Now, what happens, I mean, a capacitor stores charge which you can extract. I mean, you can cause the charges to go from the positive plate to the negative plate, creating a current, just like a battery. But the main distinction between a capacitor and a battery is that a battery creates a constant potential difference. The potential difference between the terminals of a battery is constant until it dies. But if you look at the potential difference across a capacitor, it changes as the charges are depleted. As the charge gets smaller, the potential also gets smaller. So it doesn't create a constant potential difference across its terminals. That's the main difference between a capacitor and a battery. No? Yes? Sure. No, the charges are fixed. We are putting them over there and they are fixed. Configuration, that's an R. There is no mistake, both of them are plus. Well, configuration is not plural. And if you want, I can give you a second one. No, for her only.